our next presenter for the day is Billy Godbold from CompCams. Today, Billy will be talking about beyond the specs, what to consider when choosing a camshaft. What I'll do now is I'll turn it over to Billy so he can get this presentation going. So, Billy, take it away.
Well, guys, thank you so much for having us going. I'm going to go ahead and try to put my my PowerPoint up. I've got like 3 monitors up, so if I look like I'm distracted and moving around, it's only because I'm distracted and moving around, but I'm actually trying to do the PowerPoint. So hopefully this is my good side. Let's see how this works. Okay. Okay, guys, are you seeing my screen? Well, hopefully they are.
Now we are, Billy. Yep.
Okay, that's good. Okay, so we're going to go through something called Beyond the Specs, and it's what to consider when choosing a camshaft. And we're going to go through a lot of things pretty quick. What I'm really hoping is as we go through it, go ahead, I'm going to go through it a little fast. We're going to go ahead and at the end go through question and answer so I can back through whatever we need to do. I went ahead and put this one slide in of that our marketing guys did. I want you guys just take a look at who CompCams is for 30 seconds, then you get me for 30 minutes. Well, hold on. Maybe you get me for... Let's try again.
There are duplicators. Your engine knows the difference. CompCams camshafts are always original designs, from precision engineering to premier manufacturing and unrivaled testing again and again by the most advanced engineering team and equipment in the industry. Buy the original, not an imitation. Copies might look the part, but horsepower doesn't lie. CompCams, no comparison.
Okay, well that should give you just a little look at who we are, and we'll throw a little bit of a discount at the end for this. So let's talk about what we're going to go through and what lies beyond cam specs. The first thing we're going to talk about is what profile development is. You know, one of the things that people, a lot of times you'll hear that camshafts are about the same size, they're about the same lift, they're about the same specs, they're going to run the same. Well, we know that's not the truth, and we're going to try to explain to it why. We'll go through a little bit about all the testing we do, go through a little bit through all the manufacturing and the quality. Hopefully you can see beyond what's going on in normal camshaft. You know, when most people talk about camshafts, I want to show you more than what you normally would see. And one of the most important things in that way is actually a systems approach. You know, a valve train isn't just a camshaft, a spring, a rocker arm, a push rod. These components are all necessary, but it's really a system. You know, I talk about sometimes that the valve spring is like Ginger Rogers and the cam profile is like Fred Astaire. Well, if you really think about that, it has to do everything that the low basket to do kind of backwards in high heels. So we'll go through about how this whole system works and how that is really what's going on. In part of that system, we have to talk about the components because any system is just a series of components all working together. So we'll go a little bit through lifters, valve springs, even cam cores. And I think I'm going to end here with where we're going to start, and that's material manufacturing topography. You know, Lake set a tremendous foundation on topography and materials. I'm going to build upon that, and then Keith's going to come in behind me, and he's great. But I put down here, like any great meal, you know, how a recipe turns out is very dependent on the quality of the ingredients and the skill of the chef. Likewise, valve train components require optimized material section and manufacturing techniques. So what we're going to do here is let's start in material science and then work our way back and go all the way back to the to where we started. Okay, so the materials. Okay, so the roller cam materials that we have, basically all cast iron, all flat taps are cast iron, so there's really not a reason to talk too much about cast irons. Every camshaft you've probably dealt with is mostly iron. 90, 95%, 98% of it's iron. What separates the materials is what's added to that iron. So let's go through here and look at what's added to iron in the typical roller cam materials. Go over 8620, 9310, 5160, some of the high-end tool steels, and then some of the tool steels that sportsmen use. Okay. Come here. Okay, so here's your four main materials. It's 9310, A620, 5150, and 5160. Note that the first column is carbon, 9310, 0.1 carbon, A620, 0.2 carbon, 5150, 0.5, 5160, 0.6. It's really clear that in this ANSI SAE style, the last two numbers are the percentage of carbon. So somebody tells you, well, what's 52100? Well, that's easy. It's a 52 series steel with 1% carbon. What's 8620? It's an 86 series steel with 20% carbon. So what makes the first two numbers? Well, it's what lies beyond that. So 8620, very common steel, is 0.8% manganese, 0.22% silicon, 0.5% chromium, 0.2% molybdenum, and 0.55% nickel. 5160, you can notice here I put the chromium in red. You can see that it's another 60% higher chromium than A620. We'll talk about why that's important. Okay, so 8620, a little brief history. Already went through the chemistry. This started out in World War II aircraft engines as far as camshaft. 8620 is actually a gear material, but when the guys at Rolls-Royce were building the Spitfire, building the Merlin engine, this is the material they chose for the camshaft in that. Harvey Crane would tell you that he came up with 8620. I know when Harvey was born. I know he didn't do the Spitfire, so okay. But he did adopt as a standard for roller camshafts in the performance industry. 8620 requires, to get 100 thousandths case depth, it requires 36 hours to heat treat during the carburizing oven. So basically, this means all of our 8620 camshafts have to be run over the weekend. So what happens is the guys load the oven on Friday, the last thing. They run it all day Saturday. It shuts down and cools off Sunday. Then they quench and temper it on Monday and send it to us. So when we're doing a run of A620 camshafts, kind of has to be out of our business about Wednesday, Thursday at the latest, and then it comes back to us on Tuesday the next week. Really, if you think about carburizing, if you've ever seen the old swordsmiths where they'd stick the sword into a fire, a charcoal fire, and then they take it out and beat on it and stick it back in the fire, they didn't really know what was going on. But what was happening is the low carbon steel was being penetrated by the carbon. The carbon was actually diffusing into the first 10, 20, 30, 50 thousandths of material, and that was what's creating the hardness. 8620 camshafts, the copper on it is not to do anything except for getting the parts you don't want hard, not hard. So it's kind of neat that the copper is not an enhancement. It's not to make it look good. It's to keep the camshaft from breaking when you straighten it. 9310. This is something you'll hear more about in Top Fuel than anything. If you look at it, it has a lot more chromium and 6 times more nickel. 8620 and 9310 are both considered gear steels. So basically, very, very similar. 9310 is considered a more premium gear steel. The real place where 9310 comes in our world is top fuel applications. The 6 times the nickel, I don't think that nickel steak was about being tough, but not the nickel part of it. It was the cheap steak. But when you hear tougher than a nickel steak, I think about nickel. Nickel makes the added 6 times 600% more nickel in 9310 makes it where you could practically tie a 9310 cam into a bow knot before it would break. Now, normally nickel really hurts the wear characteristics. So 9310 has the chromium. The added chromium offsets the wear reduction of nickel so that you really wind up with almost identical performance of A620 and 9310 in camshafts. The only place this wouldn't be true is where you see really, really drastic bending. Maybe a flathead Ford with a little 800 barrel that has only 3 bearings, so it's got really long spans. That would be a place where it'd use 9310. 5160. 5160 started, 5150, 5160 both started with both the aftermarket and OEs all went this way at the same time. There was a lot of metallurgists, a lot of people sitting around tables going, if we could make the best possible camshaft, what material will we use? And somewhat surprising, this is sort of what came out of it. The nice reason that what makes 5160 so good is the induction hardening lets you really tune in the heat treat. You can make it deeper or shallower. If you make it too deep, say if we decide we want to make a half-inch deep induction hardening, we can do that. The problem with it is really likely to crack, and it also makes the camshaft kind of brittle. But one of the big advantages, it doesn't require copper masking. There's two ways to put copper on a camshaft. You can put it with electric plating, or you can put it with sodium sulfide. Hold on, not sodium. Basically, good, like arsenic stuff. So basically, you really, really, really don't want to do this in your garage because it's liable to kill you. The other problem with 8620 and Nitro10 is those 36-hour carburizations. That's a big furnace going for 36 hours. So you can imagine the CO2 that's produced in this. One thing about the 5160 is how much it came out really in the early 80s, but it's amazing how much that technology improved. In fact, by the late 90s, early 2000s, most NASCAR teams were running 5160 with a quench and temper beforehand in all of their roller cam applications because it's really, really good on wear. Here's the other thing about when I talked about heat treat death. The cam on the left is an 8620. You can see the copper masking. You can see the heat case depth on it. It's only about 100 thousandths. And then you can see it starts getting really fuzzy. If you look at the cross section of the cam on the right, this one's 5160. You can see where I've done hardness checks, and you can see how the hardness changes. It's a quarter-inch deep on the nose and still over 100 thousandths deep on the base circle. This gives us a lot of flexibility on what grinds we can put on it. It also is just a lot deeper road. If you think about like your driveway going to your house, if it's concrete, it can't be thin concrete. You need to lay down gravel, pack the soil, and make sure that it's going to be good subsurface support. The 5160 cam on the right has tremendous support underneath. And you can see this with this picture of theory of it. 8620 is going to be the same depth all the way around. Any place that doesn't have copper, the carbon's going to diffuse into the surface, and you're going to get the type of profile you look on the left. With induction hardening, you're going to see more of that profile like you see on the right. I think it's really gives a lot more flexibility. If you look at that plot in between, that's the difference between a UGL, how we'd mill a lobe in blue, versus the finished grind in red. And you can see where we're taking off material, where we're leaving material. We really want to have that extra flexibility from a deeper heat treat where possible. So tool steel. Tool steel is what you're probably hearing about most in professional racing. All tools, when somebody says they have a tool steel cam, that's kind of like saying you have a black car. There's a lot of different ways to have a black car. NASCAR teams use a powdered metal M4 tool steel. So really, this isn't like powdered metal rods. This is really state-of-the-art stuff. The biggest issue with that is the material in like a NASCAR cam is $400 for a 24-inch bar, 2.5-inch diameter for PMM4. And then the heat treat is another $400. So basically, you have $800 into material and heat treat alone. Nice things is through hardening means you can't grind through the case. And because it's through hardened, you have the same compressive stresses throughout the core. The problem you might have in 8620 or 5160, if you grind 50 thousandths off one side and 10 thousandths off the other, somewhere you're transitioning between a deep case and a thin case. And where it's deep, it has more compressive stress, and when it has shallow, it has less compressive stress. So you get more deflection. That uneven loading can cause spalling from the bottom. And that's why we really want to make sure that when we're taking a core, that we grind it properly. We have actually a whole computer program that picks which core is going to take the most even material for a given grind. But what we learned from PM, we actually made new grades of tool steels. We're starting using different conventional grades of tool steels. They're excellent choices. This gives you an idea of the tool steels we tested for camshafts, just a few of them. You can see the S7 up there. One thing you're going to note really quickly is how much more alloy content. You look at A8, it has 5% chromium. That's so much more than what you saw in the other materials. S7, 3% chromium, but only 0.5% carbon. If you look at our grade that we use most, which we had a mill make for us, it's got twice the carbon of S7. So we can use that in a lot more applications than people can use the normal stuff. Look over at M4, 4% vanadium, 4% moly, 4% chromium, 5.5% tungsten. You can see why that material is so expensive. Well, let's talk about surface engineering. Lake already showed this device a little bit, but one of the things is I had a conversation with one of the guys at Cummins one time, and I was talking to him about all the material science stuff I was doing, and I was really proud of my ST4 grade that we had people make. And he goes, well, Billy, how much did you increase the ultimate tensile strength? I said, well, I've got this ultimate tensile strength up by, all the way up. It's 10% higher, 15% higher. He goes, well, what if I told you I've doubled my strength? I'm like, well, that's impossible. He goes, well, I didn't double my strength. I doubled the area that I was loading. So if you think about walking across a field that's full of snow with snowshoes versus walking on some sort of pointed toe boot, you're going to sink more with less surface area. So what we're doing with surface engineering is trying to broaden out that surface area. So there's skid profile, those profilometers like you can buy on eBay for $50, and then there's stuff like we have that costs $50,000. A little bit about RA. RA is a lousy measurement. Keith will get into this more, but if you look at the upper right-hand corner, all three of those surfaces up here in this corner have the same RA, but they don't at all have the same performance. So when you start looking at a profile like this, this would be great for a camshaft. This one here in the middle would be lousy for a camshaft. And this one over here would be kind of in between. And what we're going to start talking about is material ratios. And you can see material ratios if you just come down from the top, cut it off, and you look at how much area you're actually loading. So in this plot, this will be a 35% material ratio, or what we'll call bearing area, effective bearing area. I want you to see that this isn't just going on with comp cams. On this slide, we see two OEM camshafts. The one on the left was from the 90s. The one on the right is fairly modern, 2015. And you can see how much they've improved the surface at the OEM level over the past decade and a half. So when I said that, if you bought a product 5 years ago, it's sort of embarrassing today, that's not just in the aftermarket. The OEs are doing the same stuff. So you'll hear people say, oh, well, I've got a polished camshaft. That's going to be great, right? Well, take a look at this. This is another manufacturer that polished a camshaft, and you can see the RA here is really good. It's 16 RA, but the waviness is 131 microinches. So it's not really going to load down here in this nice part. It's going to put all the load on these points and bust out. So you can't just go up and polish a camshaft and go, hey, I've got a great cam. One of the failures we saw a lot going back from 2005 to 2015, 2016 was edge loading on camshafts. And I think I can explain it after having these gauges. If you look at this profile, you can see where the failure actually occurred. And this failure occurred on the edge of the lobe. So if you look right here where I have circled in red, you can see this spot on the edge. And so what was happening is when you ground it flat, as the wheel eroded, it made sort of a bathtub shape to the cam face of the cam. And then you would get the sharp edge of the lifter wheel riding on that sharp edge, right into that edge, and it'd start flaking there. So the first thing you'd see is a little bit of line in it, like somebody cut the lobe with a razor blade, kind of like you see up here. And then the next thing you see is starts falling out around that stress riser. So what have we been doing? We've been working on a lot of stuff with CBN and CNC grinding, and then some post-process polishing. Here's a really good flat dress on a CBN grinder. If you go back and look at what was going on in 2012, 13, 14, this was sort of state of the art for us after we changed our wheels and after we changed our dress profile. The problem with this, it was easy for it to get that edge loading. about 2016, 2017, we started to go to a crown dress on all our rollers. And you can see this is very similar, but we're slightly convex. When you start looking at this, this is 300 micro inches plus and minus. Fine talcum powder is bigger than this whole scale. But you can see how we drop about 100 millionths, about a tenth of a thousandth of an inch on both sides of the load. And that made a tremendous difference. Now, after we do that and got our dress right, the material right, got everything going, then we went to a high energy, high kinetic energy. There's three ways to polish. You can use electrical energy, you can use chemical energy like REM that anneals, but that leaves surface carbides out, or you can go to a physical polishing. Now, belt polishing isn't isotropic, meaning it leans lines and it can do things. We go through a centrifugal system that is isotropic, so it leaves a really, really nice finish. And we've been able to increase the loading of our camshafts by 2.5 times, a 250% increase in effective load bearing area. And this is the result today. You can see these bearing areas are so much higher. We never saw anything in the 90s before. Now just about everything that comes out of MSE at 20 millionths of an inch, 90% of the area of the camshaft supporting load. Now let's look at some other components. So basically, if you look at our left, that's our original, comp cams roller lifter design. And you can see when you start loading it down at the bottom that you get a lot of deflection there in the bottom. We came up with the Elite lifter that was better but still had some deflection. And then our new Sportsman was on the right. And you can see how we loaded it. We've really decreased what was going on. Basically came up, so you can see the pocket mill here. We've got a much lighter weight. We've got multiple oil paths. We've got 2 coming down the legs. We've got 1 coming from the skirt. So a lot of stuff going on in this deal. Now you'll hear people go, well, should you run needles or bushings? Well, needles are really good because they're low friction, less wear on the camshaft, and great endurance. And they have very little oil sensitivity. The negative of it is has high point loading. So if you're out of control and slamming together, you can get bad stuff like this needle and the axle can start spalling. The bearings can rapidly fail. And those needles are spinning at a really high RPM. And if you do fail a lifter, you've got all these little bits of needles that go all through your oil system and make a mess on your dry sump pump. So bushings, they're very forgiving in extreme loading conditions. People who run systems like a dirt car that might be out of control or anything with a turbocharge that runs one of those popping boost controllers, I always want to see them in bushing. When they do go out of control and they impact, it spreads out that impact. There's no way to get a needle in the oil pump if you don't have needles. And the bushing wear normally is pretty even. What's the problem with it? Well, the material in the bushing becomes super important. The camshaft is absolutely going to track more and wear out earlier because there is more friction. They're going to be more expensive. They're going to have more frictional power loss in the valve train. And they're going to be much more sensitive to what oil you run in it. But if you don't know if you're in control, it's a great choice. It's a little bit on a camshaft. Talking about the whole system. When you start loading a camshaft, if you look at this guy right here, when we load it in FEA, we're seeing 3/1000ths of bending. And it's kind of funny because if you go back to when Grumpy Jenkins changed his journal size, Bob was beating Grumpy. Grumpy goes, how can that happen? Bob was actually working harder than him. So you can see kind of what was going on. But he went to the bigger journal, got NHRA to do it. And he said, hey, my cam's 4 degrees too big. And I'm like, check it on the lifter. It's not 4 degrees too big. He goes, well, it acts 4 degrees too big. So we came back from this design to this design. And it's pretty interesting because if you look at this design, now the bending is 1/4 as much. And it's funny because that bending actually became the 4 degrees of duration that he thought he was losing. So we're going to go through, speed up, go through some conical development. Regular flat wire dampener springs, they're problems they have. They're one frequency, so they're very easy to resonate. They're simple, but they're heavy. The dampener in it creates a lot of friction, and generally they're fairly large in diameter, so you have a lot of mass. The Beehive was a great step because it had the smaller top, so you could run a smaller retainer. You had some progressive pitch, especially at the ends, so that made it not all one frequency, but still there were about 2 or 3 coils that were the same frequency. Then you had the ovate wire to kind of fit more spring in a smaller installed height, and it also distributed the stress better across area. The benefit of the conical is you still have the small ID top, but now you have tapered sides, so the active mass reduces as each time you go through. If you think about it like a football player, you have your defensive back up at the very top, and you have your middle linebacker, nose tackle in the middle, and linebacker somewhere in between. So each spring is asked to do a different task. So we can kind of like model this spring like this, and you start looking at coil 5 on this plot moves so much more than the rest of the coils. So we're doing modeling, and we can see here's the motion of each coil, and then we work to figure out what stresses each coil. Not only can we calculate this in a model through the modeling software, but we can even go in there and put a strain gauge on the spring itself. You can see it here in this picture right here. There's a strain gauge glued right here. There's another strain gauge glued right here. We've got strain gauges that we can glue on each coil, so we can actually see the exact stress of that spring at each coil. So it lets us go back and modify this pitch spacing to make sure that we even up the stress through every one. If we modify the pitch spacing, we can go in here notice the spring on the left never stops vibrating. Every time it cycles, it actually goes through there and cycles 4 or 5 times. The spring on the right, you can see that we've really, because of the different frequency, we've got much less oscillations going on. We can go, well, Billy, that's great, but that's not for race engines. That's just for, well, endurance race engines, but not for drag race engines, not for things with over 600, over 650, over 700 lift. Well, I kind of call this project Spinal Tap Junior. Ben and I were working on Spinal Tap, and after we got through, we realized that nobody except us could ever afford to do something like this. So basically on Spinal Tap Junior, we said, well, instead of 11,000 RPM, let's go 10,500. Instead of 1-inch lift, let's go 800, 850 lift. So we took this dual conical and some of the low shock profiles, and we worked with this. And you can see here's the run at 3,500, 9,500 RPM, 10,760 RPM. This is a package he ran on the dyno, and he can talk to you about it, but just an amazing deal. A 10,000 plus RPM package that doesn't cost nearly as much as something like the 1-inch kind of pro stock type applications that we've worked with. Okay, so I've mentioned low shock a couple of times. I guess I need to talk to you guys about what is low shock. Well, this part of the presentation is about how to learn to relearn to compare cam lobes and select the camshaft with a very asymmetric profile. So how are we all taught to compare profiles? Well, we're taught to just look for lobes with a similar duration at 50 and lift. Find the one that was the smallest it could be at 20 thousandths lift and as big as it could be at 200 lift, and that'll always make the power. So the smallest at 20 and the biggest 200 was always the best choice as long as it didn't leave exit wounds in the valve cover. Okay, well, Billy, how can that possibly be wrong? Well, we knew exhaust lobes didn't follow that rule, just the intakes. 2, we didn't understand that the opening side and the closing side had very different things going on. And 3, we didn't really think about what really limits the duration that you select for an application. So what do I mean when I say what really limits the duration? Well, normally you'd think, well, minimum and maximum RPM. Well, okay. The other thing you start thinking about is piston to valve. And that's 100% true, both in the race and street. The intake opening side is always going to be tight on any good engine. Number 3, definitely on the street, idle stability and emissions. If you open the intake too far, too fast, you're going to have real trouble with idle stability. You're going to have real trouble with hydrocarbons on any emissions test. Number 4, low RPM performance. What we didn't understand is low RPM performance had 100 times more to do with the closing side than the opening side. High RPM performance. We're really going to talk about this more. So let's look through what happens at each valve timing point. So here's the complete cycle, the way I look at a camshaft. You can see the power stroke, the exhaust stroke, the intake stroke, and the compression stroke in all 4 events. So exhaust opening, you note, it happened in the middle of the power stroke. It didn't wait till the bottom dead center. It's like in the middle. As soon as you open the exhaust starts to blow down. You get to empty the chamber and then start back over again. So all of the exhaust that gets out around bottom dead center, you sort of get out that for free because you don't have to push it out later. But as soon as you open the exhaust, you've stopped your power stroke. So now none of that energy, all that energy is for pushing out the exhaust now, not for pushing down the piston. So here's a graphical representation of that. You can see in this application, the exhaust opening is not even midway. It's around, 280 degrees, 290 degrees before top to bottom dead center. So you can see that all of this first area is where we're getting in the power stroke, and then we get the free exhaust. So we have to look at those two quite separately. So what's the next event? Well, the next event is the intake opening. So as soon as you open the intake, you start your overlap. The remaining pressure in the chamber, what you're trying to do is time that exhaust wave out. So when it gets to the end of the collector, it's reflected back. So you have the positive wave going down your header. It hits the collector. It's reflected back as a negative wave. And you want to set the length of the exhaust system so that negative wave arrives back at the exhaust valve to create negative pressure in the chamber when the intake opens. So basically, in emissions, this is kind of like a little EGR. If it's cracked a little bit, you can actually do some good things to emissions. You do need to know that this whole thing works together. So the exhaust opening is the highest pressure. That's the beginning of your wave tuning wave. Then everything else kind of is triggered off that super high pressure. Now, where people would get a little goofy about this is looking at overlap. You can see that you can get all caught up with this peak piston velocity that occurs about 70 degrees after top dead center. And so where do you open the intake to try to get peak lift there? If there's a limit to how quick you can open it and you want it open as much as possible there, that's why you got the Ultradyne type deals that delayed the I/O and then went super fast. And I kind of joked with those that, if you slap the spring really bad, you get into some issues. So we try not to do that. The intake closing is the most important deal in this whole combination. Is once the intake closes, the air stops moving through the port. Earlier intake closings are better for low RPM. Later intake closings are better for high RPM. But one of the things that we want to see is, check this graph out. You look at the first graph, you see the momentum keeps filling it well past bottom dead center. As soon as you close it, now you start the compression stroke. But how I showed in the second graph on the right, that lift at bottom dead center is super important because there's a lot of flow there. So let's see how we'd use this. Here's a plot in blue of a normal big block Chevy drag race cam with a normal profile compared to our new low shock lobe. And you can see the new low shock cam has the earlier EO, but yet the steel piston and valve, but a much later intake closing. Now, when you go for a low shock opening, it doesn't mean that you're going slow the whole time. It just means that you compress the system before you really get after it. One of the things we'll call it sometimes instead of a slow shock is a crack and whack. Get everything going and then really push harder. That's why you have the same area on the opening side, even with that slow early opening. But because if you think about the spring as your dancing partner, and think about marriage, you've heard happy wife, happy life. Same deal with this. If I can go a little slower early, keep the spring from doing that surge that we saw in the video, then I can ask more of it on the backside and get this earlier intake closing that I'm talking about with the same backside area. But now with this cam, you're actually going to have a much earlier intake closing, so it's going to act like a smaller cam. So what can I do to avoid that? Well, what I can do is spread the lobe separation out a tiny bit, 1 degree, go to something with a little more lift to get a little closer to coil bind, add 4 degrees duration, and then all of a sudden I'm picking up all of this backside area with the same intake closing. So this cam looks like a slower camshaft, but it actually makes a lot more power, and it allows you to put a bigger camshaft in it with a slower lobe without hurting it anywhere. Now you guys are going to go, does this stuff really work? Well, here's a test that Jeff Smith just posted to Engine Labs here on the 12th, and he did this test at West Tech. He took our best LS cam from a couple years ago and then compared it to our brand new Low Shock cam. And here's the power difference. Note that we're up, this is similar spec camshaft, left to right. I welcome you to go look at the article. But you can see that we're making 16 more horsepower and we're carrying out easily an extra 500 RPM. So basically, I run a little over, but I appreciate you guys letting me do this. Here's the conclusion question. I want you guys to know that's AER Save 10. If you buy anything on our website, there's already some discounts, but you can save additional 10% or something like that if you do the AER Save 10. And let us know how we can do questions.
All right, Billy, we got a couple questions that came in.
Okay.
What about a turbocharged engine which may have a greater intake manifold average pressure than exhaust manifold average pressure?
Yeah, that's a great question. What's going on with turbo deals? Our first question when somebody calls in a turbo is, what is your boost to back pressure ratio? A lot of the stuff you read about turbo cams, read David Vizard's books from the 80s, they had 3 or 4 times the amount of back pressure to boost. Today, what you're seeing is that normal camshafts for professional racing turbo systems where you have that 1-to-1 ratio or even less to 1-to-1 ratio through most of the pull, they wind up looking a whole lot like the same camshaft that you would see in a normally aspirated motor. Where the real difference is, these will be different. 1 second, I may have unplugged myself. Yeah, I did. Where the real difference will be in these is that the ones with the good turbos is they'll be slightly shorter duration, because all of a sudden now the cylinder head that we thought flowed 400 CFM, because you've got such a more dense charge, now it acts like that is that's a 500 CFM head or 1,000 CFM head. It's like drinking Diet Coke versus drinking a Frosty. I hope that helps.
Okay, our next question, as they keep coming in, do you favor an asymmetrical exhaust lobe with a more aggressive opening over a gentler symmetrical lobe?
I've played with that a whole lot. A lot of times we were going with, if you look at our CPX series and our NXX series, those are definitely like that. They're a little slow very, very early, but they get after it. Once the valves open 50 thousandths, they go really, really fast. Where you get in trouble with that is if you took a top fuel motor that has has less stiffness in the rocker arm and has tremendous exhaust pressures, you can't get back into the throttle at 50 thousandths. That valve's probably not even off the seat. So you really have to go with it depends, it's very application independent. Another thing is guys running sprint cars run really fast exhaust lobes. And the problem is if you run a fast opening exhaust lobe is the guys who do it well normally have a wall full of either headers or a wall full of collectors and links they can play with. Because when you open the exhaust really fast, you wind up making that waveform very, very sharp. So if you think about that, when you make it really sharp like that, you wind up with it coming back and being very, very strong, but not very broad. So a fast opening exhaust is going to be very header sensitive. Where if you take a more symmetric type lobe and run it on the exhaust, not truly symmetric, but more symmetric, it becomes much easier to tune because it's going to have a slower wave opening. And so when it comes back, it's not going to just be, if you're a 20-inch header and a 30-inch header and a 32 and a 34, if you have a real fast opening exhaust, it's going to want one of those and hate two of those. If you run something like an XX profile that's very smooth or XNX for a newer one, it's not going to be nearly as sensitive on the exhaust opening.
Okay, our next question is, what do you do differently when speccing a performance diesel camshaft versus a performance gas camshaft?
Well, that's a pretty interesting one. A performance diesel camshaft is going to normally be much, much smaller. You know, you'll see guys that'll go in there and go, hey, this diesel goes almost 4,000 RPM. It probably needs a 230 duration camshaft. Well, the problem is if you put a 230 duration camshaft in it, you're going to have to put on tight lobe separation to get to tune there. If you do that, you're going to carve up your piston so bad that your combustion efficiency is going to be horrible. So unless you're running like nitrous, propane, and 60 pounds of boost, those big carvings that carve out that you've done in the piston is going to tear the thing to shreds. So you would just absolutely be shocked how well, because of all the boost, because of the density of the air, how well short camshafts, 188 at 50, 191 at 50, 200, 205 at 50, a much smaller camshaft becomes very, very good. And that's where some of the stuff that we're doing with this low shock technology and the new cam designs is extraordinarily valuable, because if you learn, making a big duration camshaft smooth is easy because you've got a lot of time for the spring to recover from the opening to the closing side. When you start making really short duration camshafts and try to put a lot of area in those, that's a much more difficult problem to solve.
Perfect. Okay, our next question is, cam bearing and journal clearances. It's a two-part question. Say for
this is a great one.
Say for a 2-inch journal size, what would be the minimum oil clearance you would run on, say, an LS at about 5,000 RPM?
Okay, I'm going to tell on myself. We had LS bearings, 2165 bearings in a NASCAR block, and I messed up and put a camshaft in it with big block Chevy bearings in it. And we ran an entire durability test before I figured out what I screwed up. After that, I was totally convinced there's only one reason that you want, one reason and one reason only you want tight clearances on a cam bearing, is you're talking about the inside of the bearing to the outside of the camshaft. The only reason you'd want that tight is because of windage on the crankshaft. So, you can run 2, 3, 5, and never hurt anything in the world except for a guy running 5,000ths clearance on his camshaft to the shell. He's going to have a lot more windage. He's going to have a lot more oil fall down than a guy running, 1, 2, 2.5, 3. So I get really nervous with very, very tight clearances. We see that all the time in our world because racers like to run a little bit of extra crunch on their blocks. So if they're doing an LS, they're like, hey, I'm going to run this with an extra 0.5 crush. And when they do it, it makes the inside of the bearing tight, and then they run a standards cam size and it tries to seize on them. I've never, ever seen a failure because the guy was running too much clearance on his camshaft.
Okay. Next question. How does an inverse radius lobe compare to the low impact lobe?
Almost any camshaft that you'd see for a small journal, like a small block Chevy 1868, big block Chevy 1948, 1949, almost every one of those roller camshafts is going to have some section of it that's inverted radius of curvature. In fact, because remember when I talked about the low shock, I called it the crack and whack. Well, that's actually pretty difficult to do in a small block Chevy or a big block Chevy, because if you're going to go slow at first and then catch up, it's really hard to catch up. The reason I think low shock took a long time to come around, people were playing with this technology in the Glidden days and doing really well with it. But as springs got better, what happened is we just didn't have enough ability with standard rocker ratios and small journals to use slow fast, to ease into it and then go. So we kind of had to just get a running start. And if you think about an NHRA Superstock guy with a 50-pound flywheel revving up to the moon and dropping the clutch to get the car off the line. Very similar. This is the type of things that people had to do. They ran really fast openings and a lot of lash because they couldn't get energy into it. As we have higher ratios now and we have bigger journals, we can do some things we couldn't do before. So the low shock stuff is definitely better on the 50, 55, 60 millimeter journals than on the standard journals, but we're using it some on the small blocks and had some very good success. It sure does like a little more rocker ratio though.
Okay, next question. What do you consider to be the maximum allowable surface chatter around the face of a lobe?
To talk about that, you really have to go how you're going to measure it. The best measuring tool I know is on the AGCOL, and it's a fast Fourier transform. They call the program Spectrum. And generally, you'd be surprised that maximum chatter you can have is about 10 to the minus 6 inches. So it's a extraordinarily small amount of chatter. If you can look at a camshaft and see chatter that's down in the 10 to the 7th inches. So if it has the same chatter all the way around it and you get fluorescent lights, you get on a good table, you can actually see chatter down in the 10 to the 7th. So if you see visual chatter, there's probably an issue. And especially if you get an eye for it, you can see where you have problems. What's funny is we used to think it was servo chatter in the CNC grinders. Sometimes you get in there where actually the camshaft between centers and the grinders starts to vibrate. And it's kind of a very interesting deal because we started seeing different chatter on different lobes on a CNC. It's like, well, that can't be a servo. And that really brought us in. So we changed all of our grinding wheels over on our CNCs. They used to be steel hubs. Now they're all carbon fiber hubs. And that carbon fiber has just enough, really not compliance, but it actually has enough absorption of high frequency that it takes out a lot of the chatter of the camshaft in between centers or in between steady rests.
Okay, our next question is, how does lifter roller wheel diameter affect lobe profile choice?
Like if you have a bigger cam journal or a bigger lifter wheel, it really lets you go to a little bit quicker profile. And the reason being is you get less torsional vibration of the camshaft. We didn't talk about this in this presentation, but I did in my AETC a couple of years ago. The camshaft doesn't turn at constant RPM. On an NHRA Pro Stock, when they were going 11,000 RPM, you can see on intake opening it gets slow all the way down to 8,500, and then on intake closing it speed all the way up to 13,000 RPM. It's crazy how much torsional vibration you get in the camshaft. As you go to a bigger wheel, you put less pressure angle into it. It creates a little bit less of those torsionals in the camshaft. So one, you want to have a camshaft that's designed for it. We use a master suffix. So if you go from a 50 millimeter cam with a 750 wheel, that'd be an R suffix. If you did it with the 850 wheel, that same, it'd be an RG. If you did a 60 millimeter with the 850, it'd be an MG. And if you did a 60 millimeter with a 950, that'd be an RH. So we went ahead and made different designs. So the tappet moves the same. The bigger wheel, you need to have a cam design for that wheel, but it does allow you to perhaps move up just a skosh on aggressiveness and move down just a skosh on duration. When I talk about skosh, like 2 degrees.
Okay, getting to our next question here.
By the way, great question, guys. I mean, those are tremendous.
Is it better to run a lower lift cam with a higher compression on a naturally aspirated street engine, like 11.5 to 1, 588, 570? And can I still achieve 6,500 to 7,000 RPM rev limit with conical springs?
Okay, last question, yes. Now let's go back to the first question. Lower lift doesn't, what's funny is that peak torque is peak air demand. So generally, as long as your head is still going up in flow, you want to maximize the valve spring lift. So if you have a spring like a conical that's designed to run 625 lift, you don't want to run at 575s because now instead of being 50, 60 thousandths combined, you're 110, 120, 130 thousandths combined. So you got to be careful. You kind of want to pick, if you're going to run 550, 575 lift, you want to pick a 550 or 575 lift spring. Now, the thing is a lot of people think the extra lift hurts them, and I have never seen extra lift hurt on the intake side. There may be some turbulence deals, some really old heads where I think I saw it, but I'm not even sure. If you ever watch John Causey has this video where he sticks his finger into a port when it's running, you start realizing you don't have steady flow to that port. It's not like a flow bench. So basically, if you want to run 575 lift, that's great. The head may not really, there's a lift to diameter ratio. So in a 2-inch valve, you may not get a whole lot going from 575 to 625, but try to run the lift around the spring. And I really don't think you'll see any correlation between compression ratio and lift. You'll see a difference between compression ratio and intake closing, but not compression ratio and lift.
Okay, looks like we got time for one more question, I think.
Well, I'm sorry I ran over on my part of it. I tell you guys, I really enjoyed it, and I'm loving the questions.
No, it's great. We got a lot of good questions coming in. Here's a question. Does LSA really matter for EFI to carburetors on LS engines?
90% of it's no. Usually you can't put the lobe. The reason that carburetors generally like tighter lobe separations than EFI is that airspeed matters through a carburetor more than it does through an injection. Now you're pulling me right outside of my bailiwick and put me right into Ben Strader's, so be careful here. But you need that air moment, you need that air volume, you need that momentum, you need that charge, you need that signal through the carburetor to get the boosters to work right in a carbureted application. The EFI system, you really just need the air in there. So sometimes on the carburetor, that extra overlap put some more air, and it made the carburetor much more responsive at low RPM with a real tight lobe separation and more overlap. Now you asked about LS in specific. The interesting thing about LS, unless you change the pistons, you really can't put a lot of overlap in an LS without crashing the valves in the piston. You violate the space-time continuum. You made a cam and a cam in the valve. Things blow up. It's bad. You don't want to be there. I've been there. It's ugly. So if you don't have room anyway, then the camshaft becomes exactly the same. If you're not changing the piston on an LS, the carbureted cam and the fuel injected cam are the same. If you do change the piston, it just depends on how interested you are in low RPM throttle response. If you need the absolute most, say you're dirt track racing and all the passing, it's a really tacky track that you run at, all the passing comes out of the corner, you're going to need a tighter lobe separation to make that carburetor work the best it can with throttle position changes. And I think that's one thing that as an industry we don't talk about enough. Engines normally aren't run like they are run on a dyno. On a dyno, they're loaded. They go up to a certain RPM, they stabilize, and then they accelerate very smoothly. In the real world, we're always changing throttle response, throttle position, and that creates something totally different. So to get that throttle response that you want, the lobe separation will be tighter because that carburetor needs more overlap because it needs more air going through it to atomize, to pull the fuel through the booster, to atomize it well, and to make it work. The fuel injection is going to be pretty dumb. It's going to go, I don't care how much is going through my throttle body. I just care how much you told me to give at this RPM in this throttle position.
Okay, we actually got time for We actually got
Okay.
time for a couple more, Billy, if you got time.
Sure. Oh, I love it. This is my favorite part. I hate the presentations. I love Q&A.
Gentleman's asking, he's heard that the racing turbo motors are running higher compression ratios now. Older days 8-to-1, now I hear 10-to-1. How does this affect the cam profile?
It really doesn't change the cam profile. I mean, the thing is people think, oh, goodness, I'm running 20 pounds of boost. I can't run the 6-to-1 compression, 8-to-1 compression. My son is working on his PhD in combustion right now. He's specializing in diesel, but he knows the gas pretty well too. It is absolutely amazing. It is not uncommon at all to see people run super high compression ratios with E85 and even higher compression ratios than you'd think on gasoline. The more nitrogen you put into the chamber, you cool it down. As you put more and more fuel, there's things that are going on in a turbocharged motor that don't go straight over. So you really don't generally don't change camshafts very much based on compression ratio. The reason we put a little bit, you see bigger cams with higher compression, is because bigger cams act super bad at low RPM without compression. So that's why you see this cam needs 13-to-1 compression. What that really means, you read it, is if you put this cam in something that has 10-to-1 compression and it doesn't have boost, and you try to go full throttle at 3,000, it's going to misfire and be a pig. But under wide throttle, we saw this when NASCAR dropped back from 15-to-1 to 9.5-to-1. That basically the cam durations, we thought they were going to change 10 degrees. They changed 2 or 4. And they only changed 2 or 4 for the very low RPM stuff.
Okay. Our next question here is, and they say it might be a little bit off topic, but they were wondering if you could address the mythology of rocker axis perpendicularity to the valve
Yeah.
stem. That's a long word for me.
I know exactly what I know exactly what he's asking. Yeah. When you look at a rocker arm sweep, here's the rocker arm of the valve. Where does it get perpendicular on the valve, and where does it get perpendicular on the push rod? And this is all about design rocker ratios. And T&D has one school of thought, and the Jessel guys have another school of thought, and other guys have different schools of thought. And if you ever want to get into something that's like a religious argument, get into that argument and say, hey, which one of these guys is right, which one of these guys is wrong. As a cam designer, I've actually learned to work with any of it because we deal with overheads, the finger followers, and they sweep different on the opening side and the closing side. So all of a sudden you get really good at designing at the valve, and you can do a coordinate transformation, go back to what you need in the cam profile to get the valve to do what you want to do. The engine only responds to what the valve does, not to what the cam does. So I can fix that where it works any which way. Now, if I was going to design a rocker arm, I'm going to tell you that I'd probably have the tip go perpendicular somewhere between 30% and 50% lift. The reason I want to go perpendicular then is because I know that's when the push rod loads are the highest. And so I want that rocker arm to be as stiff as it possibly can be at that point. I want no wasted energy. Likewise, I probably want the push rod either close to perpendicular, somewhere between the base circle, because then I get the least wasted motion, to about half lift. And so even though it doesn't make the most constant rocker ratio, something that goes perpendicular on both sides around 30% lift is what I personally like. Now, if you personally like something else, I still want to sell you a camshaft, and I absolutely positively can design around any rocker geometry system that you can imagine. So it doesn't affect me, but as far as if I had to pick a church of where to be, I would be close to 25-30% perpendicular on both sides.
Great.
And sorry if that was inside baseball to some of you guys.
Well, I'm glad you knew exactly what the question was before I finished.
Yeah, it's a hotly debated. There's about a dozen people that care very vehemently, and there's about 1 million people that don't even know what's going on there. And I wish I was in the million, not the dozen, but oh well.
Okay, our next question is, I'm not seeing Low shock cams for cathedral ports. Would the LSR cathedral port cams be a better choice over the rectangular port LST? And how specific are the cams designed for the individual port designs?
Really, they're not. We do have a low shock cam for the budget cathedral port deal. It's called a drift cam, but it's not. It's a 54778-11, and it's for a real inexpensive budget type deal where somebody wants to use our new LS6 Plus spring. I think its part number is 26906-16 or 26906-kit. That system is a beautiful system for somebody who's trying to take a junkyard motor and make it into a race motor. But honestly, I've sold a bunch of people that are running 5.7s, the 54-301-11. That's our smaller of the LST kits, and that runs amazing in a good, in a 5.7, 6-liter cathedral port engine. I think it probably actually runs better in that than it does in the LS3, and we probably should have marketed it different. But it's just a super all-around camshaft and a cathedral port.
Okay.
And definitely beat on sales to get more of those because I love making those packages. They're kind of fun.
Okay, our next question. At one time, inverted flank or peanut lobes on roller cams was the craze. Is this still the case? And if yes or no, discuss the merits and disadvantages.
Like I said kind of earlier, that almost every roller camshaft for a small journal is inverted. Now, what's funny is I wanted to come up, when I started at Comp Cams, all of the extreme energy hydraulic rollers are inverted flank lobes. And I mean, they're inverted as much as the grinder will make. But when we did the XE cams, I wanted to call them IR cams. But Scooter said, "Oh, you can't call them IR cams. People think IR cams blow up." The inverted race curvature isn't what blew up anything. What blew up people's engines with the early IR cams, those peanut lobes, was how quickly they went into the inverted flank section and out of the inverted flank section. So sometimes cam designers learn a new technique and they get a little greedy and they try to take full advantage of it. The inverted section usually is pretty happy, but how quickly you get on the gas and how quickly you come off the gas going into that inverted section and going out of that inverted section determines the harmonic content of it. It's what causes it to go crazy. So basically, any lobe that you see that's specifically designed for a small block Chevy, a small block Ford, or big block Chevy size journal, that cam is inverted. We just don't talk about it because inverted got a bad name, so we don't really promote it very much. Now the thing is some of the early attempts at inverted race of curvatures, I know Crane had an IR series that like had skulls and crossbones on it, and our TK series is really, really inverted. Some of the early attempts at inverted camshafts, we probably pushed things a little more than we should have, and we probably got ourselves in a little bit of trouble. But the inverted is not the cause of the trouble. How quickly we got in the inverted and how long we stayed before we got out. And it's very much like driving a road race car. How soon you get on the gas, how rapidly you roll on the gas, and how soon you get off the gas going into a corner on the brake. If you allow the car to transition, it's very, very smooth. Even though you're already on full brake and you're already on full gas at some point, it's how well you how you change the car from full brake to full gas. Very much with the inverted flank. The inverted flank doesn't break anything. How quickly you get on the gas to get to full, and then how quickly you get on the brakes. If you make that transition too quick, you will upset the valve spring. You'll let everything go into loft, and the problem with loft isn't loft. Loft's great. It's kind of like jumping the ramp over the bus if you're Evel Knievel. Jumping's great. Landing can be bad.
Okay. Next question. Low shock lobes and street durability for a daily driven vehicle, say about 10,000 miles a year. Is there a durability issue, or is there a threshold that makes you nervous?
No, absolutely, positively. If I was going to put anything in something I was going to try to drive 10,000 miles, 100,000 miles, it would absolutely be a new low shock design. They put so much less early deflection. They're so much easier on lifters. They're so much easier in valve springs. To give you an idea, on a bracket race car, I took a guy who was going about 25 to 50 passes. He changed the springs at 400 passes because he felt guilty. And his lifters look better, the cam look better, everything looks better. You'd see the same thing on the street, that the low shock is definitely the way to go. You know, which low shock cam, that could be interesting on what you're going to do, but 10,000 miles, that's not going to hurt these things at all.
Okay. And then our last question we got here, and then we'll give away some more prizes. On a roller cam, how large of a pressure angle is used on really aggressive cam designs, and how large of an acceleration value has been successfully used?
Well, you know, here we really need to talk about acceleration values at the valve, not at the cam, because really the cam doesn't matter. It's how fast we're accelerating the valve. So, but let's start with pressure angles. Pressure angles, when they get much above 30 to 33 degrees, they really tear up lifters. I did one with the Briggs that was 40 degrees. It broke the lifter the first time we turned it over by hand. The old NHRA super stocks, and they were running stock journal sizes in the small block Chevys, they were up around 31, 32, and blocks would only get about 40 or 50 passes before they just trashed the lifter bores in them. Clearly, once you start doing some good clawed stuff and you start putting good bushings in it, you go a little bit more passes. But once you get past 30 degrees, it really, really tears up lifter bore angles. Now that journals are bigger, I can tell you that it may have been, I've never looked at the pressure angle on an NHRA Pro Stock lobe, you know, because they're always 60 millimeter plus journals. They never have high pressure angles. I know when you reduce the pressure angle with a bigger wheel that your torsionals are less, but it's really not the driving factor in anything. Now, going back to the first question about the lobe accelerations, you know, you start looking at it, and does it really matter what the peak acceleration is? Because remember, when we're doing these high lash lobes, non-low shock, we might only be running 3.035 inches per degree acceleration at the tappet, but we were running 35 thousandths lash, and we were crashing the thing early. So you had huge dynamic accelerations. So who's to say that you can't run 20, 30, 40% higher tappet accelerations if you don't have all of this compliance, and you don't have all this crash? And some of the NASCAR teams have measured deflection. We've measured push rod loads. We can see kind of what's going on with deflection with the laser, with prox probes. And I can tell you that the valve acceleration isn't nearly as limited by tappet acceleration as we really thought it was. That we were getting double and triple the valve acceleration that we thought we were getting because we were like a pole vaulter. We were running up there and we were jamming the pole into the pit and making it bend and storing all this energy and then slinging ourselves up. Now that we're putting that pole in smoothly, we can run much higher accelerations later. So, you know, being an extra 10, 20, 30%, 15% wouldn't even be a break-even point. That, you know, you'd see, that's why it's hard to do low shocks on small journals where it's easy to do on big journals, because I can't run an extra 20% higher acceleration on a small journal, but you really can on LS and definitely on modern engines.
Okay. Billy, thank you for your time. Great presentation, great answers to the questions. If you guys didn't get your question asked, remember we are doing a roundtable at the end, so we will be asking some of those questions to our panelists at the end.